welcome everybody. It's great that you could all join us today. And so once again, I'm Kevin Biggie, and talking to you from St. Johnsbury, Vermont, in the USA. And we're happy you can join us today to talk about an optimized installation system for renewable energy generation transformers. So as far as our agenda for today, I'll begin and we'll take a look at some industry trends related to renewable energy and renewable energy transformers. Then I'll talk about some challenges specific to renewable energy generation transformers. And then the next section is a solution, and that's what the webinar is all about, is a solution to the challenges related to these kinds of transformers. I'll specifically focus in on one particular solution, which is a new not so new paper that Weidmann makes as a solution, which is called INSULutions DPE paper, and it has several different benefits. One in particular is the fact that it has a higher thermal class. So I'll talk about that in a separate section, and then I'll hand it over to my colleague Alexander Levin, who is going to cover some interesting transformer design concepts, specifically by applying a higher thermal class installation paper like our Weidmann DPE paper. So, and then we'll wrap up with a summary. So, talking about renewable energy, and so we all know that renewable energy is really growing and taking off. The graph on the left is just a simple illustration of how, for example, wind and solar have grown just in the century from next to nothing in 2000 to, being a significant percentage of renewable energy generation. Whereas hydro and other renewables have held rather steady. And on the right, you can see actually a picture from a recent news release of the world's largest to date solar farm in China, which is 3.5 gigawatts. So renewable energy is, as we all know, growing and continuing to grow. So now let's talk about the transformers for renewable energy. So what do these things look like? So first of all, these kinds of renewable energy sites can have lots of transformers, hundreds of them, in fact, per site. And the other thing is that they're getting larger. So they can oftentimes be rather large in size, several thousand kVA and above, for example. Also voltages and the BIL ratings of these transformers are increasing. And typically these transformers are also constructed with what we call a layer type winding. And some of the bigger ones are, again, in excess of approaching even 10,000 kVA and higher. So they're bigger, higher voltage, and they're typically layer winding transformers. Great. So when we talk about challenges specific to these kinds of transformers, so first of all, they're intermittent. So the load going to these transformers is intermittent. So the sun doesn't always shine and the wind doesn't always blow. So there's a lot of on and off, so to speak, character to the load that these transformers see. And typically, currently, to deal with that kind of variable load, these transformers are designed with quite a bit of extra capacity. And so there's oftentimes some excessive capital investments and a bigger footprint needed in order to deal with that. And when you have transformers that are perhaps oversized, if you will, then even when the sun isn't shining or the wind isn't blowing, you can have a lot of no load losses, losses from the transformer just sitting there, so to speak, with losses in the transformer core specifically. So and then finally, as Frankie can attest to, in the deserts of Arizona, these sites can often be in hot places. So in particular solar farms, but other ones as well. So when you deal with transformers being in a hot ambient situation, that can reduce the lifespan of these transformers and reduce their reliability. On the right there is a simple graph that's just taken from an IEEE standard on solar transformers, for example, and you can see the dotted line number 3 is kind of showing, you know, an on and off character. So basically from about 8 in the morning until 6 p.m. at night, these transformers are loaded to around 100%, and then at night they shut off. So, and talking about some other challenges. So these transformers are also typically connected to inverters, and so the power coming from the solar panels or often sometimes windmills are going through inverters. And when the power is coming through inverters, you can have harmonics and other power related situations that really increase the thermal, the electrical, and the mechanical stresses on these kinds of transformers. And another thing is with these, again, layer type transformers being larger, so they are insulated typically with paper. And I have a diagram next, we'll show this in a little bit of detail, but these larger transformers, layer wound, layer type windings with lots of paper, the paper can take a long time to dry for the manufacturers when they're made in the factories, and a long time to impregnate with liquids. So you can potentially have some quality problems just due to the size and you know, the nature of these bigger units. And then finally, too, getting bigger in size, these transformers are also not only larger in size but also higher in cost. So these are all the challenges. When we talk about layer type winding transformers and paper insulation, this diagram is just trying to depict that. So here you see, for example, a layer wound transformer where you have the low voltage winding, part 1 on the inside, and then you have the high voltage winding in the middle and a second part on the outside. But the majority of the solid insulation separating all of those layers of conductor is paper. So you have paper between the layers, you have paper between the layers in the low voltage and in the high voltage, you have paper that is at the ends of the coils. You can sometimes have extended paper between the high and the low to provide a barrier. Paper between the high and the low as pack out, so to speak. So there's lots and lots of paper in these big layer wound transformers. So when we talk about solutions to these challenges for these specific types of transformers, and the fact that they're layer type transformers largely insulated with paper, you know, this paper, this one component of a transformer is actually pretty key and important to defining the size and the weight and the footprint and ultimately the cost of these kinds of transformers. The paper also defines heavily the losses and therefore the efficiency of these transformers. And ultimately the paper is the key thing that defines the long-term reliability and resilience of these transformers as well. So with the insulation paper being the key, if we had a so-called engineered paper solution that has enhanced properties, you know, such a paper could provide some opportunities to optimize the performance of these kinds of units. So a paper that could perhaps withstand higher temperatures, a paper that can perhaps dry and impregnate with liquids more quickly at the OEM factory, a paper with improved dielectric performance, you know, and can help reduce the size and weight of these transformers. And most importantly, a solution that is cost effective, right? Every solution is always a balance between performance and cost. So a cost-effective solution in particular can not only help with all of these challenges, but can actually do it and actually help reduce the cost of these transformers overall. And so with that, I'd like to introduce you to our specific paper solution, which we call our Weidmann INSULutions DPE paper. So DPE is standing for Diamond Pattern Enhanced paper, as opposed to the typical craft DPP or diamond pattern paper. And so this paper is a special grade of layer insulation for liquid immersed layer type transformers. And so we've engineered this paper to still be made of cellulose. Okay, so it's not kraft, right? So typically, the paper that's being used and has been used for a long time is kraft paper. Kraft meaning coming from softwood trees, trees with needles. So we have found some special and unique mixes of other celluloses, because there are other sources of cellulose, um, and those special mix of fibers and the way that we process the paper um, yield some performance advantages over the typical 100% kraft paper. Yet, because it's cellulose, still the cost point for this paper is also still very, very effective. So in particular, the four benefits that I'm going to cover today in a little bit more detail about this paper and what it does, and then specifically what it can do for renewable energy transformers, is it has four advantages over the typical kraft paper. So number one, it has a higher thermal endurance in both mineral oil and ester liquids. So that means that it ages more slowly and it has a higher thermal class as a result. It dries faster. So you can potentially have higher quality and productivity when these transformers are being made in the factory. It also impregnates with dielectric liquids faster, similarly quality and productivity improvement potential. And then finally, it has better dielectric performance. And so you can potentially improve your dielectric insulation design with this DPE paper. But again, just to talk one more time about the cost again, that's the important part of this paper as a solution. So if you look at the solid insulation in a typical layer one transformer compared to all the other materials, core steel, conductor, the liquid, and other, the tank and such, the solid insulation is really typically representing just a couple percentage of the cost of one of these transformers. And so with DPE paper being 100% cellulose, again, we've kept the cost down, and all of these benefits are achievable at a relatively small price difference on the overall transformer cost, which we say is typically less than 1%. So to get into these particular features and benefits of DPE paper, I'll cover them one by one. So first of all, it dries faster. And we say that typically DPE is drying up to about 30% faster than typical 100% kraft papers. And so we've confirmed this in many different ways. We've done several types of laboratory tests. We've done, we did a special study on full transformer coils with a partner, a company of ours, Hedrick in Germany. And on the right, you can see a picture of that particular study with a test coil in there. And to the graph underneath the picture, you can see that the blue line is representing measurements of power factor during drying over time, and the blue line representing the DPE coil, and the green representing the kraft paper coil, and the DPE coil is clearly drying more quickly. We've also done studies of actual layer wound transformers in OEM factory dry out processes in their factory ovens, and we've also confirmed this to be true. So faster drying, again, it leads to potential quality improvements, less failure rates in the factory, less initial moisture to start with. So the fibers that we use are generally drier to begin with than kraft. So there's less moisture to remove, and overall this could lead to potential productivity improvements, which as we know, capacity of making these types of transformers is important, and so anything that can be done to make more of them is definitely a good thing right now with all the growth seeing in renewable energy transformers. The next thing is that it impregnates with dielectric liquids more quickly, and so so we've studied that. in particular, we did a test where we took some liquids and suspended a piece of paper in it, and then heated the liquid and put the whole thing in a vacuum chamber, and we measured how quickly the liquid is rising through the paper. And again, that's where we found that DPE is able to impregnate about 30% faster. With both mineral oil and ester liquids. So again, this is another opportunity to improve productivity in the factory, to improve quality, and in particular for transformers like this that use ester liquids, which are more viscous and can take longer to impregnate. DPE is ultimately an excellent solution. The third of the 4 benefits of DPE paper is that we designed it to have better dielectric performance as a layer insulation in layer wound transformer. So we completed an extensive electrical testing series that took several years to do way back when we were developing this paper, and not only studying the breakdown of the paper in AC voltage, but also for the first time measuring partial discharge inception of layer insulation paper, as well as impulse breakdown. And so the combined results of this study, looking at PD inception, AC breakdown, and impulse breakdown, is that we developed a special set of insulation dielectric design rules specific to DPE, which we can bring to our customers to help with their dielectric design. And so there's the potential to reduce clearances and to ultimately optimize size and cost due to the improved dielectrics with DPE. And then the fourth benefit of DPE paper I'm going to focus on a little bit more specifically, and that's going to be the subject of the rest of the webinar, and that is that DPE is a higher thermal class paper. And so let me talk a little bit about that. So when we talk about DPE being a higher thermal class paper, so that means it ages more slowly and it has longer life at equivalent temperatures. And the way that you determine the thermal class of these kinds of materials is one of the popular ways is to do what's called a sealed tube accelerated aging test. So you can see some pictures on the right where you see that's a picture of our aging lab with our aging ovens and the aging sealed tube containers, and also a container itself with all of the contents opened up before it. But when you do an aging test where you test the conventional system of mineral oil and thermal upgraded Kraft versus a new system, we did that according to this IEEE standard C57100, and we found that DPE in mineral oil has a thermal class of 130, which is 10 degrees C higher than TUK in mineral oil, and in esters it has a thermal class of 140. And again, even these accelerated aging tests take years to complete. And when you do these tests, what they result in are these so-called life curves. So this represents the tensile strength retention equivalent to the standard system of TUK and mineral oil of these other systems at elevated temperatures. And then you can extrapolate those back to normal temperatures at the IEEE lifetime of 180,000 hours in order to calculate the thermal class. And so that's where we get the thermal classes from. And so what you can do with this higher thermal class is you can actually design your transformers differently. And so in particular, there is a graph about the temperature limits available using IEC terminology, and on the right using IEEE terminology. But just to point out, TUK and mineral oil again is 120 system, whereas DPE in mineral oil is 130, and DPE in ester liquids is 140. And so these graphs in these standards represent what you can do from an average winding rise design and also from a hotspot maximum capability design aspect as well.